Well, hi, everybody, and welcome to another recorded Zoom interview, this time with Dr. Gary Smith down in New Mexico. I assume that's where you are, Gary. Is that true?
That's right.
Okay, what's the weather like down there? Is it Albuquerque?
In Albuquerque, today we're looking at low 50s and sunny. The sunny
Hey,
part is usual. The low 50s is about 10 degrees warmer than average.
that sounds pretty good about right now in late December. Thank you. I just met you 2 minutes ago via Zoom, but I'm familiar with your work and have been my whole career here. I started in the early 90s, and you were doing a fair amount of work in the Kittitas Valley and in central Washington and probably beyond back in the 80s. So we should put a disclaimer right in off the bat that you haven't been thinking a lot about this area for that many years, I'm guessing. And in fact, you're maybe not teaching geology anymore. How does that work? Been going on with you lately?
Well, it has been an interesting career. I've been here at the University of New Mexico for 37 years. Most of that as a professor in geology, or we call it the Earth and Planetary Sciences Department here. But I also got involved a lot in doing faculty development and teaching work with faculty, and took on being director of the faculty development programs, and then
Hmm.
ultimately shifted my faculty position to something called Organization, Information, and Learning Sciences, which abbreviates as OILS. It sounds like maybe I still did geology. And then I actually finished my career up to retirement just a few months ago as an associate dean in the medical school, running all their professional learning programs for faculty and physicians.
Oh, my gosh. Well, congratulations on your retirement. And yeah, let's go back to, I don't know, maybe coming out of your PhD work in geology, did I see you went to grad school in Corvallis? And is that where you learned some volcaniclastic techniques that you were doing in the Ellensburg Formation?
Yeah, I guess for deeper context, it might seem odd for somebody growing up in the suburbs of Cincinnati, Ohio, but I became infatuated with volcanoes when I was about 12 years old. And so my whole pursuit of a geology degree and undergrad at Bowling Green State University in Ohio, and then on to do graduate work at Oregon State, was really driven by a desire to get involved in volcanology.
Hmm.
And so when I started into the graduate program at Oregon State, mentored by the late Ed Taylor, I I really wanted to get involved in some aspects of the Cascades, particularly since it was right following the eruption of Mount St. Helens in 1980. I started in grad school in 81. It seemed like the time to get into doing things in the Cascades. The other thing I came to appreciate right away, and I hope you won't take offense with your igneous petrology interests, but I came to realize that to become a volcanologist in academia really meant you were going to fill the igneous petrology position on the faculty. And to become an igneous petrologist, in most cases, you had to have what I call an analytical gimmick. You had to run a lab of some sort, a geochron lab, ICP-MS lab, an XRF lab, something. And that was not me. I didn't even change the oil in my truck. My advisor, Ed Taylor, nicknamed me Sadim. That's Midas spelled backwards because every time I stepped into the XRF lab, something bad happened and I wouldn't know how to fix it. So I knew that being an igneous petrologist and an analytical gimmick was never going to work. And it was never the geochemical petrological side of volcanology that really interested. It was more the physical processes. And
Mhm.
so thinking about it that way, I very quickly came to appreciate building off of the work that Ed Taylor and his students have been doing out in the Deschutes Basin area of Central Oregon for a number of years, that sedimentation around volcanoes was not very well understood. Um, Sedimentologists would tend to think about typical approaches to interpreting fluvial sedimentary sequences and would move towards volcanoes and move into a whole slew of chaotic, poorly understood facies, lots of poorly sorted stuff, the things that were just sort of in a garbage can way called lahars, and said, well,
Right.
we'll leave that to the volcanologists. The
Uh-huh.
volcanologists, on the other hand, would start up on the top of the mountain and would come down. And once it became more fragmental stuff than lavas, they said, we'll leave that to the sedimentologists. So there was this wide area of opportunity where I realized there really wasn't very much research done. There have been some geomorphic sediment transport studies done around active volcanoes, but this idea of what does a volcaniclastic sedimentary record look like next to a continental margin arc, nothing.
Huh.
So my work in the Deschutes actually got me a fair bit of attention because I was putting together ideas and models about process sedimentology in these arenas that very few people have thought about, but immediately saw application of elsewhere. And so you're right to say that my interest in the Ellensburg was born out of my dissertation work in volcanoclastic rock farther south.
Well, living here and visiting the Natchez Grade and the Nile Basin and Craig's Hill and Ellensburg and out by Thorpe, I mean, these deposits, even if you have no interest in geology, you're drawn to those beautiful outcrops. And so it makes sense to me living here, but I suppose in general, sure, it was kind of a blind spot for many people between those two disciplines, as you say. So can you frame it for us just a little bit? What's the wheelhouse or the time frame that we're talking about for your work in the Ellensburg Formation? And what do you remember most vividly about some of those features or deposits in central Washington that you ultimately produced a number of papers upon?
It's interesting you mentioned the time frame because I often look back at that time and realize it was probably the most productive research episode in my entire career. Because the nuts and bolts of the work in the Ellensburg was done in about 10 months.
Hmm. Wow.
It was supported by a postdoctoral fellowship through what I think is now associated with Western universities, but at the time was NORCAS, the Northwest College University Association for Sciences, associated with Hanford down at the WSU Tri-City site in Richland, as
Mhm.
well as the Basalt Waste Isolation Project, which was the big geologic endeavor at Hanford at the time. And as a part of the site characterization for Hanford, for the BWIP project, there was a need to have a much better understanding of the whole tectonic framework of the region. And so they realized most people working at Hanford at that time were also basalt stratigraphers and petrologists. And they really felt like it'd be great to have somebody who took my expertise in the volcanoclastic sedimentology and applied it to looking at the Ellensburg west of the Hanford site.
Hmm.
And so it was really funding from those sources that were going to fund this postdoc, which was really meant to only last a year. Um, and actually was sped up in part because I got a faculty position at the University of Arizona to teach for a year and needed to pack up and leave.
Hmm.
So it really amazes me when I look back on it how much the pieces fell into place. I had a great field assistant, a fellow named Marshall Deacon, who had just finished his undergrad at Oregon State in the
Hmm.
spring of, what would that have been, 83, I guess, or 84.
Mhm.
And it was just so great to be out in the field and commuting back and forth because the Department of Energy didn't really want me staying overnight or camping someplace with the Department of Energy rig. That was a bad PR. So they really expected me to commute from Richland out to the Ellensburg outcrop areas every day.
Hmm.
And so it provided great opportunities. Marshall and I would just brainstorm through things on those drives back and forth. Sometimes on the drive out, I say, no, I was thinking last night about this and that. So maybe if we went there, we could figure that out. So we would actually figure out the day's field agenda as we were driving to Yakima or Ellensburg,
Ah,
wherever we were going
ah,
for the day. And then on the
yeah,
way
yeah.
home that night, excited about how the pieces were coming together. And so I look back and I'm amazed at how many publications came out
Yeah.
of a project that only had about 10 or 11 months of data collection.
Well, let me show the viewers a few of these, and I'm going to share my screen right now, Gary, and then maybe show you a couple of maps that might jog a couple of memories. So yes, I mean there's kind of an original paper that's kind of doing some terminology type things, and then the 1987 paper is kind of new to me, but that was going carefully. Um, I just did a field video that I'm about to publish on I was visiting the rattlesnake outcrops and then kind of tried to compare them to the Natchez grade, and I was happy to see that you were doing that with Marshall. And of course, this is the one that really most everybody here continues to know about and continues to think about. So maybe this is where I'll slow down. There's a few other papers as well, of course, but is maybe where I want to slow down and drill down a little bit with you. Again, thinking about stuff for the first time in 30 plus years. Um, Viewers, we're doing a deep dive, and in this winter's Cascade A to Z live stream series, we're going to put this context together. So if you're watching this cold, I don't expect some of this to work for you, but I want to take advantage of the time we have with Gary. So here's Ellensburg and here's Yakima, and these are these major basins that are full of the upper Ellensburg Formation. And then in this classic 1988 paper from Gary, we have potential sources. So Gary, I guess my first question is, when are you, my first question is, can I visualize an incredible apron of Ellensburg Formation blanketing everything and having these sources, whether it's these or these, filling this entire map with thick upper Ellensburg?
Actually, my guess is that it didn't completely bury the anticlines. Um,
Okay.
and the reason I say that is that we do see basaltic conglomerates interbedded with the volcanoclastics in the proximity to some of the anticlines,
Oh, that's
which
right. Yeah.
suggests that they had developed sufficient topographic relief
Mm-hmm.
to be local sediment sources. No, probably nowhere near as much relief as exists between the ridge tops and the valley floors today, but they were there and would have kept the apron from covering the whole area uniformly. But your use of a term apron, I think, is right on target.
Thank you. And do you have some names in mind? Like, were you suspecting Old Scap Mountain and Pear Butte and a couple other these random places that I think I remember from Paul Hammond? Were you carefully studying the sources, or you were mostly playing in the sandbox down here?
We were mostly playing in that sandbox, but
Yeah.
one thing that was interesting to me in terms of developing my work with volcanic classics is that for both the Deschutes Formation in Oregon and working in the Ellensburg in Washington, the source areas weren't there to see. And while that wasn't the motivation for my study of those volcanoclastic rocks, it was this idea of, well, in many cases, volcanoclastic sedimentary sequences may be the only records we have of volcanoes that we no longer see.
Right.
The Central Oregon Cascades at the end of the Deschutes Formation time in the earliest Pliocene subsided into an intra-arc graben and got buried under younger stuff. But up in central Washington, it's just the opposite. The uplift of the Cascades stripped away, at least at that time. I don't know if anyone's found anything subsequently, any of the proximal volcanic edifices that would have fed all this acidic detritus down into the Kittitas, Natchez, Yakima, Sela areas.
Hmm.
And so it certainly was of interest to me to think about how can we maybe pinpoint where those were. So that the black areas, polygons on that map, were
Yeah.
essentially taken from mapping that had been done by Roland Tabor, Paul Hammond,
Yeah.
Jeff Clayton, and Joe Vance, um, and sort of identified places where there were high-level dacitic intrusions that at least had the mineralogy that
Mm-hmm.
would match up with Ellensburg detritus, because
Hmm.
the Ellensburg debris, from a petrographic standpoint, is very homogeneous over several million years of record. It's hornblende dacite and some
Hmm.
silicic andesite. Um, some pyroxene, rarely any biotite. I mean, it's just really monotonous that way. But there aren't very many rocks that match up with that that could be of the
Right.
potential right age. And some of those black dots, black polygons in that map, at least at the time we were working in the mid 80s, Joe Vance and Jeff Clayton had dated, mostly using apatite fission track approaches, and they were significantly younger.
Hmm.
Um, Roland Tabor had some, I think, potassium argon dates and some things up northwest of the Kittitas Basin. And those may very well line up for sources in the Kittitas, because I can't remember the exact ages on him. I think he had dates around 12 or 13 million, maybe 11. But the Ellensburg up in the Kittitas Basin seems overall older, at least
Hmm.
started earlier. That dacitic volcanic debris is interbedded with Grand Ronde Columbia River basalt. So it was underway by 16 or 17. Whereas down at the latitude of Yakima and Natchez, the interbeds in the Grand Ronde are all actually represent what was probably the Columbia River pushed all the way over to the western edge of the Columbia
Yeah,
Plateau.
yeah, yeah.
And the real big flux of stuff came in post 12 and extended up bits and pieces to maybe as young as 7 or 6. But at that time, there just wasn't anything known of that age. Um, and I didn't have a budget for geochronology, and it was not cheap to come by.
Right.
But we went up and sampled some of those plutons in I shouldn't recall them, they're more plugs, very high level intrusions, not big plutons, in the Bumping Lake area that had not been dated by the UW folk. And it was actually the Division of Geology, or DNR in Olympia, that gave us a small grant while I was teaching for that 1 year at the University of Arizona. They had a world-renowned potassium argon lab, and they gave me a dirt cheap deal to crank out a number of potassium argon dates out in the Ellensburg, as well as we dated a couple of those plugs, and one of them at least lined up very well
Hmm.
to be a potential source. So there's probably others up in that neck of the woods,
Yeah,
especially given the duration of Ellensburg deposition. There should have been several volcano lifetimes involved, but that's
right.
sort of where we left it in the late 80s.
Sure. Um, this you're doing great. Thank you. This is just what I was hoping for. What should I visualize if I see some big, nice, fat lahars and they're traveling tens of miles out of the Cascades and getting to Ellensburg and beyond in the Ellensburg Formation? Don't I need a significant slope to get that stuff going? Like I'm not imagining just a little dacitic plug, but I'm imagining truly a stratocone the size of Rainier. Is that where I should be mentally?
It may not need to be as big as Rainier. I mean, the plug would essentially be, underneath some sort of an edifice. I always thought Mount Hood made a really great analogy,
Okay.
in part because the last 30,000 years or so of volcanic activity on Mount Hood, which has been concentrated on the south side, has seen multiple episodes of the growth of dacitic dome, which mineralogically, color-wise, and everything looked just like Ellensburg, but
Ah,
just kept collapsing and falling apart, and essentially developed a big debris apron that forms the ski slopes on the south side of Hood and filled all the river valleys for some distance. You know, the last eruption there in the early 1800s happened just before Lewis and Clark came down the Columbia,
yeah.
and the debris was coming out the Sandy River in front of them as they were going down the Columbia River. So that stuff gets transported out fairly far. Debris went all the
Mm,
way down the White River
mm,
to the east side of Hood too. So I've always thought the type of volcano, because the other thing that's characteristic about particularly the Ellensburg and the Yakima and Natchez area is, yeah, there's some pumice around, but not very much.
mm,
It was just a lot of lithic debris, and that's the sort of thing you get when you build lava domes and they just keep collapsing and collapsing and collapsing into block and ash flows and getting mobilized with rain or snow melt and moving on out as debris flows. Um, some of the deposits up around Thorpe and Ellensburg are very much more pumice rich
mm,
than what you see to the south. And
mm.
I don't know what the outcrops look like along Highway 10 near Thorpe now, but at that time, there's some really great volcanic debris flow deposits there in the road cuts that actually had blocks of pimicious ignimbrite in them.
Yes.
And that suggested a very different kind of eruptive style, more pyroclastic flows, of the pernicious sorts of things that happened early in the Mount St. Helens eruptions in 1980, in contrast to the dome building eruptions later. So although I don't know the people have really looked in detail at differences in the petrology across the Ellensburg Formation, but I would suggest that the eruptive behavior of the volcanoes that were active a little bit earlier in feeding into the Thorpe Kittitas area was
Mm.
different from the ones that mostly got underway later and fed debris through the Nile Natchez Yakima area.
This is great. I mean, there's been hardly any work since your time here. I mean, that's part of the reason I know about your work because, there hasn't been 30 plus years of work since. couple of undergrad theses and that sort of thing, but nothing to the level and the breadth that you were doing. Am I hearing from you right now, again, through the decades of remembering, that the deposits in the upper Ellensburg Formation in the Kittitas Valley are distinctly different in many ways from those basins closer to Yakima, and therefore are you visualizing a different source? I know that wasn't the main point of the work, but you mentioned that Cooper Pass area. That was a pointed source, it seemed, in the 1988 paper. Do you recall that?
We were thinking that, and just looking at paleocurrent data and so
Yeah.
um, you got the impression that the stuff that came into the Kittitas Basin was coming from the northwest. And the
Mm,
Cooper Pass plugs were located well. Tabor's
mm,
ages made sense.
mm.
Um, and so, there may have been others as well that we don't
Yeah.
really know very well, but they seemed reasonable. But one of the things that always impressed me about the outcrops in the Ellensburg Thorpe area is just how much more pumice rich they were than the
Yeah.
deposits to the south, suggesting that the
Mm,
volcano that has the volcanoes that were feeding that were had a very different kind of eruptive behavior.
yeah. Why are they so it is pretty dacite rich, both in the Kittitas Valley and down to Natchez and the Nile. Why is it so monolithologic?
Well,
Does
it'd
that
be really interesting for somebody to go in and look at it more carefully, petrologically. Um, that was so different from what I worked with down in Central Oregon in the Deschutes Basin. Extremely, not only did you have a sedimentary record there, but a lot of interbedded lava flows and pyroclastic flows. I mean, my
mm,
volcanic stratigraphy I pieced together down there included about 100 different ignimbrite and lava flow sequences. And that ran the whole gamut from basaltic andesite to rhyolite. And
huh,
so then to come up to the Ellensburg, and it's just
yeah.
the same sort of boring um, stuff, which was also made it more difficult from a stratigraphic standpoint. If there were changes in the petrology of eruptive material that were visible in
Right.
phenocryst content and so forth in the field, it would
Yeah.
really help you piece together the stratigraphy using more than just what you could walk out physically. So I
Mm,
do think it would really be interesting, especially because there's got to be multiple volcano lifetimes in there. It's not just one slug of magma that came up in the crust and sat there.
right.
It
Yeah.
had to be a repeated recipe that this kept getting repeated over and over and over in those areas of crust where the magmas were ascending, that just kept producing the same stew at the end.
Mm,
Um, and it is, for such a long period. I mean, I encountered something similar, but on a shorter time period when I came down and started doing work in New Mexico. One of the areas I worked with has a very big record of rhyolite volcanism that's entirely monotonously the same.
mm.
But we also found out once we got it dated that even though there were, dozens of different volcanic events recorded there, and there were probably 20 different holes in the ground that we could identify as potential sources, they were the same petrologically down to the last rare earth element.
Mm.
But they all came out in only 500,000 years once we got the geochronology done.
Oh,
So we
right.
realized that what happened in that case is it was probably a batholith that instead of being erupted in one humongous ignimbrite caldera collapse eruption, got tapped by about 20 different straws that bled all this stuff off and threw it all out in the countryside before
Yeah.
any additional assimilation or fractionation had taken place to mature the magma. But
Ah,
that model doesn't quite work for Ellensburg sources.
doesn't seem like it, does it? Um, so I just did an interview this morning with a guy named Mike Eddy, who came in 10 years ago as a grad student into Central Washington and started doing very precise geochronology on some of the tephras, Teanaway Formation, if you remember the Teanaway and the Swak. And he solved so many problems with timing, and this correlates with that, and this is impossible, and this must have come in later. And it was just the improvement in the geochronology that allows that. And I'm guessing the same is true in our topic today. Like it would seem that these basins would just be ripe for these highly precise dates. Do you agree? And what major things could be worked on in the next couple of decades from a new crop of geologists with your deposits that you were working on?
One of the questions or concerns that a lot of times geochronologists and petrologists have in working with volcanic plastic sequences versus the primary lava flows and tuffs is, you know, you have mixing of stuff from different ages and origins. And so it's not quite the same to march through the section at Natchez Grade west of Yakima and collect samples for geochemistry or petrology
Right.
or geochronology rather, and kind of piece together a petrologic geochronologic story as going through a stack of lavas or a stack of ignimbrites somewhere.
Yeah.
But I would argue that particularly now that I want to say the geochron is cheap, but it's easier and faster to do a
Yeah.
lot of these techniques. Take the risk because um, what we found, for instance, in doing a fair bit of argon-argon work in some volcanoclastic sequences down here in New Mexico, is that even though you're analyzing detrital materials, the ages very systematically get younger up section.
Mhm.
There's just no question you're tapping this stuff and dumping it out there shortly after it's being erupted.
Mhm.
And so I think it's worth, you know, there are some primary fault tephras. So you certainly focus on those, but I think particularly pulling out the pumice constituents out of the sediment, you can analyze just a few pumice clots now and get enough stuff to analyze. It's unfortunately
Sure.
they only have sanidine in them, or you could do single crystals like we did down
Mm.
here. But
Mhm.
it's still I think it's worth the gamble to say, let's just assume that this stuff and the sedimentary facies imply that too. We're redepositing this stuff very quickly. That doesn't mean that there isn't some stuff from older eruptions that gets mixed in, but I think going through a stratigraphic section with a combined geochronology or geochemistry program would be a valid way of trying to get a handle on just how monotonous were these day sites. Maybe they look more monotonous than they really are. We maybe
Right.
can get some handles on the petrologic processes that would have led to producing still something that's not terribly varied in composition. It would be more obvious petrographically. But I think that if someone's really interested in sort of thinking about what leads to such long-lived monotony in a dacitic system, you know, the geochronology that exists in the Ellensburg suggested about 5 million years of boredom there in magma genesis. Is that really true?
Yeah. Yeah.
Or is there something there in the details and a more detailed geochronology would tell us what's really happening?
Mm. Love it. How about one more little area of our discussion, and that's probably enough today, Gary. I've started this series of programs this winter on the Cascades, and we're starting with the basement, and then we're getting into accreting a large igneous province, and we're trying to keep track of different units at different times. And I think a major theme that we will continue to work on over the course of the winter is uplift and trying to figure out we're not just building a birthday cake. We've got these major uplift events where we suddenly lose a bunch of stuff, and now the oldest stuff is exposed at White Pass, like some of that basement is at White Pass. Is the Ellensburg helpful in regional correlations ultimately leading to major uplift events? And if so, is it possible to remove Yakima fold and thrust belt uplifts from Cascade Arc uplifts? Because I feel like there might be, I can't decide how many uplifts we've got at present. And it would be nice to be able to realize when we have major uplift chapters in the Cascades, and if we can remove that from the Yakima fold and thrust belt, that'd be wonderful, but I'm not sure that's possible. How can the Ellensburg help with this uplift story?
Well, I've tended to view yeah, I appreciate the Yakima folds, particularly the farther south you go into and across the Cascades. And so some of that history is obviously discombobulated together.
Right.
Um, but I've unless the past 30 years plus of research has shown otherwise, I've always kind of gotten the feeling that it's difficult to know exactly what structures were responsible for uplifting and bringing the older tertiary and even pre-tertiary rocks to the surface in central and northern Washington Cascades. But that's always seemed to me to be, on the whole, different from the east-west compression in the Yakima Fold Belt.
Mm.
Um, what I will say that the Ellensburg has a couple of things that can contribute to the uplift story, and I think this information is probably in the 1988 GSA bulletin paper.
Okay.
We did a lot of cobble counts, not so much in the debris flow deposits, but in the fluvial conglomerates, where the rivers were really flowing on their normal regime without getting completely inundated with volcanic debris. We did a lot of cobble counts. And what we found in the Yakima Natchez, sort of the ancestral Natchez River drainage, if you'd like, during Ellensburg time, is there's a lot of dacite in there. Okay, so let's set that aside out of the pebble count data. In some cases, there's a fair bit of basalt. Let's set that aside. What's left? Well, what's left is mostly older volcanic materials, which we assumed is Feist Peak, Stevens Ridge. Well, Stevens Ridge is now part of the Feist Peak. It wasn't back then.
Yeah.
And in some cases, you get some lithified, greenish, toughy looking things that look Gohana-Pakashi. And but what you find when you actually look at those constituents, even though they're relatively small, and the pebble counts as a percentage, but we did generally 200 pebble count, is that the ratio of the silicic looking stuff to the andesitic basaltic looking stuff increased as you went up section,
Mm.
which we suggest is maybe showing on roofing during uplift. The streams are
Oh,
coming
wow.
down through the Pikes Peak and getting increasingly larger amounts of the older, more silicic stuff. And then the coup de grace is there's the youngest piece of Ellensburg close to Yakima. Took me a while to figure out. And we refer to it in the GSA bulletin paper, I think, as the Pleasant Hill gravel.
Mm.
It's exposed, I think, along a road called Maple Way, particularly well, so northwest of Yakima, on the north side of the Yakima Ridge exposures. And what's interesting there, and the reason it gave us a pain, is it's mostly a pile of fluvial conglomerate without a lot of debris flow deposits in it. And we finally realized it's actually a paleo valley that was incised into the earlier Ellensburg, late in Ellensburg time.
Oh,
It has the youngest vertebrate fauna of the Ellensburg in it. And we knew where that fauna came from Jim Martin's work, and we sampled tephras close to it. And sure enough, it was a little bit younger than the rest of the stuff there at Natchez. Most of the stuff in the Natchez grade sections was like 10 to 11, 12, sits on top of 12-million-year-old Pomona. But that stuff on the Pleasant Hill gravel is closer to 7.5, something like
mm.
that.
Mm.
Those gravels have pre-tertiary class in them. Not very many, but stuff that looks like it came from around Rimrock Lake Inlier. So it kind of goes with this unroofing idea that we thought we were seeing in the older part of the upper Ellensburg, maybe digging down through the Feist Peak and into the more felsic stuff and even some of the greenish Gohana-Pakash stuff. And then by 7 million years ago, streams had found their way into the pre-tertiary inlier up there. So, of course, a stream can cut down through younger stuff, but it's going to be hard to really get the motivation to do that if it's not being uplifted.
Yes.
So I do think we are seeing an uplift during that sort of 12 to 7 million year period.
Mm.
And that the Rimrock Lake inlier of pre-tertiary rocks were exposed, at least in some places, at the surface by 7 million years ago.
Well, that's music to my ears because we've been kind of working with that kind of logic anyhow. The Tieton andesite flow is coming right on to this arcosic melange of the inlier, and I'm just openly saying, well, why wouldn't we have that stuff naked in front of God and everybody at 3 million years ago when those eruptions are happening? So that will be continued to be a major area that we're going to be thinking about this winter. Gary, it's been a real delight chatting with you. I don't know if you wanted to add anything else here at the end about your work. I know it was so long ago, but I showed up here in the early 90s and I learned from a fire hose, aka Robert D. Bentley, who was just giving me all sorts of information. And your name was filling the air in the early 90s. Gary Smith, because you had just been there a few years earlier. I don't know. Let's finish with that. Did you collaborate much with sweet old Bob, or you must have a little bit, at least in the field?
Well, that's interesting, and maybe a little bit of historical context you might find interesting. I credit Bob for first getting me inspired to even think about the Yakima Fold Belt. Again, I came from Ohio. We
Yeah,
always heard about the Columbia Plateau basalts.
right,
I
right.
had this vision of Eastern Washington being this flat, featureless plain of
Yes,
basalt. And actually, when Mount St. Helens erupted in 1981 or 1980, I was a college junior, but again, very infatuated with volcanoes. And I actually got press credentials from a paper in Ohio and came out during the week right after the eruption. Got to fly for search and rescue missions with the National Guard and drove around to Yakima to see the tephra, and it was a complete whiteout of ash. And I remember saying, I'm so confused because you're driving and trying to see through all the ash that stayed suspended by the wind in the air. Here are these big ridges. And it's like, what in the world is this? This is supposed to be a flat, featureless plateau.
yeah.
So when I started graduate school in September of 81, there was a big multi-day regional AGU field trip looking at Columbia River basalt from the coast onto the plateau and finishing actually with the regional meeting in Ellensburg. And Bob led part of that and really opened my eyes to thinking about this enigma of this fold and thrust belt that's sitting here at right angles to the orientation of the continental margin. And that remained a big interest of mine. I even speculated on origin for it in an AGU abstract in San Francisco in 1982, associated with rotation of the Blue Mountains block due to basin range extension and things like that. So I was always indebted to Bob for first sort of inspiring my interest in those things. But by the time I came around to doing my postdoc work, there was some interesting politics involved. I always liked Bob. I interacted a great deal with his good buddy at the time, Noel Campbell. I don't know if you know
Yeah.
Noel down in Yakima.
Sure.
Noel did a lot, helped me immensely with the Yakima work. But it all comes back to the sort of the politics of the time with the basalt waste isolation project.
Oh,
And one of the big concerns at that time was, when did the Yakima folds form? Because there was a group of people, and Bob was very vociferous in this group, that said, well, all the folding and faulting happened after the CRBs were erupted, and therefore the strain rates are very high and still represent an important constraint on seismic stability for the Hanford site. A lot of the Hanford geologists had been demonstrating how the basalt flows were thinning over the folds and following into the synclines and so forth, indicating the folds were forming the whole time, just they just kept getting buried. So there was a bit of tension because Bob was actually doing consulting for the Nuclear Regulatory Commission, which has a very strong, critical eye on things, and was
yeah.
driving the people at Hanford nuts. And one of the reasons that the Hanford folks were interested in supporting my study was, what evidence is there that the Ellensburg Formation was affected by the development of the folds? And the answer was
Oh,
hugely. The
yeah.
folds were definitely forming during Ellensburg time. So there
Right.
was a bit of that. Well, you can't hobnob too much with Bob because he's on the other side of the fence. Well, but I
Wow.
still think very fondly of Bob and how he helped me appreciate that the Columbia Plateau is not a flat, featureless plain.
Oh, that was great. Just like it's the early 80s all over again. I can feel, I can taste the tension in the air. That's beautiful. Thank you. Well, Gary, thank you. I'm going to stop the record button here and then hold the line. We'll just chat for another couple seconds if you don't mind. So thank you for your time today, Dr. Gary Smith. Thank
Thank
you.
you.